Today we're going to continue talking about sequences and series. We talked about sequences last class. Now we're moving on to the series aspect of it. Well, what is the difference between a sequence and a series? Basically, a sequence is separated by commas. 1, 2, 3, 4, 5. A series is separated by plus signs. 1 plus 2 plus 3 plus 4 plus 5. But the numbers make a sequence. Okay? So, on the paper in front of you it says if A of n is the sequence of terms, we now define S of n, S sub n, as a series representing the sum of those terms. Now, this one has an n on it. The n means there is a finite number of terms to be added. Okay? So S sub n is equal to the sigma, starting with 1 and going up to n, of A of I. In other words, A1 plus A2 plus A3 all the way up to AN, whatever the last term is. But since AN is the sequence of an infinite number of terms, we're now going to define an infinite series as just a plain S, as the sum of an infinite set of numbers, all the way up through AN and then continuing on. Now, sometimes an infinite series is written by given the first few terms and then a formula for the nth term, which is called the general term. And we've seen the phrase general form, general solution before. It's kind of a generic sort of thing. It still has a variable in it. For instance, the sigma from n equals 1 to infinity of 3n would be 3 plus 6 plus 9 plus ... plus 3n. So they stick the formula in the middle of the sequence, in the middle of the series when they write it out. Okay. Now, what is the difference between a converging sequence and a converging series? That's what we're going to talk about next. It says an infinite sequence that converges has the nth term approach a limit. So in other words, you're doing the limit on the sequence rule, whatever that explicit rule is. If that sequence rule approaches a number, it's going to converge. And that's what we talked about last class. Okay? If you get a number, it's going to converge. If you get an infinity, it's going to diverge. Now, what about an infinite series? An infinite series that converges has the sum of its infinite number of terms approach a limit. Now that sounds a little bit strange. How can an infinite number of things add up to be a number? It can, in some instances. Okay? Let me give you an example. Okay? Let's talk about me standing up here and the door being way over there. Okay? And that is 1 unit of distance, whatever 1 unit is. If I walk halfway to the door, how much distance have I covered? Half, okay? If I then walk half the distance again, how much of the total distance have I now covered? 1/4 of it. Does that make sense? Mm-hmm. So first I went a half of it, then I went a fourth, then if I went half the distance again, what would that be? An eighth. Are you seeing what I'm doing?
Oh, like, so like you're half, but then half of that half.
Right. Half of each half as I keep going. So that is a series. If I was adding up all those distances, that would be the series of a half plus a fourth plus an eighth plus a 16th and so on. Now, am I ever going to get to the door?
Yes. Yeah.
In theory, not really, actually. You're just getting closer and closer. If you could get down to the micron quantum level, there's still always a half a distance to go. But when you add up all these distances, the limit is 1. Does that make sense? The sum of all of those distances together is going to be 1. So I am going to, in limit terms, get there. Just like it was when we learned limits at the beginning of the year. Limit is something that the graph approaches but never gets there. Now we're talking about the limit of a sum. Okay, and the sum being, after my 2 first moves, I've covered 3/4 of the distance. Then I've covered 7/8 of the distance. We're going to do this whole problem in just a minute. But the limit here of the sum, as n approaches infinity, of the sum is 1. The limit is 1. And that is going to converge. Okay? So that's how an infinite number of things can actually have a sum. And it has to do with how the numbers work. Now what we're going to do is we're going to look at some that diverge. And sometimes when it's divergent, it's real easy to spot it. You just look at it and go, well, of course, if I add up all the terms in this sequence, it's just never going to get close to, it's never going to get to a number. Let's take a look at this first one. N equals 1 to infinity of 2 to the n. Let's write out a few terms. Plug in a 1. What's the first term going to be?
2.
2. Plus, what's the second term? 4. What's the third term? 8. The fourth term? 16. And so on. If I add up all the terms, is it just going to keep getting bigger and bigger and bigger? Yes. The more terms I go, the bigger the total sum is going to be. Agreed? Okay. So this one diverges. It says explain why these series are divergent. It is because each term is increasingly larger. If the terms are getting bigger, it's going to diverge. It's just pretty obvious that it is. If it's a single unit, it's not a fraction, it's a single unit and the terms are each getting bigger, you can't add them all up and get an answer. It's just going to be getting bigger and bigger and bigger.
But if they get bigger, like if it's a definite number where infinity is, then it would be convergent?
Not, okay, the sequence can converge if they're getting bigger. But the series won't because you're adding up all the numbers together. Okay? Because they have a picture of it on another page, but if the graph is getting bigger and then it's leveling off like those logistics did, you're still adding in 10 or something close to 10 plus something close to 10. Let's say 10 is the top. Something close to 10 and then 10 and then 10 and then it's still getting bigger and bigger and bigger when you add them up. But the sequence itself is leveling off at 10, but the series is not. The series is still diverging. Okay? All right. Now let's look at the next one. Let's write out the first few terms of this sequence. If I plug in a 1 for n, what is the first term going to be? 1. What's the second term? Square root of 2, and then square root of 3, square root of 4, and so on. Okay? Are each of those terms increasingly larger? Is the square root of 2 bigger than the square root of 1? Yeah. Is the square root of 3 bigger than the square root of 2? Yes. So these are getting bigger, not as fast as the other one, but they are getting bigger. Okay? So each term is increasingly larger. Again, I'm going to go ahead and write this out, increasingly. Even though it's growing slowly, it's still growing. And so when you add on the next term, it's getting bigger and bigger and bigger. Okay, what about cosine of n pi? If I add on the terms of cosine, what's going to happen to those terms? They're going to keep changing all over the place. Let's take a look at this. What is the cosine of 0 pi? 1. What's the cosine of 1 pi? -1. What's the cosine of 2 pi? 1. What's the cosine of 3 pi? -1. What is this thing doing?
Oscillating.
It is oscillating. Is it ever going to converge? No. Okay, it is oscillating. Oops, let's write this correctly. Oscillating and will not converge. Oscillating ones do not converge. They don't. Number 4 says series that are convergent are much harder to spot. Show that these are convergent series. Let's take a look at number 4, the summation from 1 to infinity of 1 over 2 to the n. So plug in 1, what do you get? 1/2 plus. Plug in 2, 1/4, plug in 3, 1/8, plug in 4, 1/16. This is the one I was just talking about. Agreed? Okay. Now, what we're going to do is something I started to do, but I wanted to do it more here. S1 means the sum of the first 1 terms. What's the first term? 1/2. S2 means the sum of the first two terms. So what's 1/2 plus 1/4? 3/4. Okay, now take that 3/4 and add on the next term. That is 7/8. So 7/8 and add on the next term after that. 15/16. Okay, now this is the sum up to a specific point. So now what I want to do is write the pattern for the sum. Okay, now notice that the denominators of each of these are the same as the denominators were for the original problem. Agreed? So that means the denominator is still 2 to the n. So put a 2 to the n on the bottom. Okay, how does the numerator relate to the denominator? It's 2 to the n minus 1. It's 1 less. Very good. Okay, and now it's asking me to take the limit as n approaches infinity. Okay, if I leave the fraction as it is, it's going to be infinity over infinity. Agreed? But I can break this into two separate fractions, and it's going to make life a whole lot easier. So what's 2 to the n over 2 to the n? That's 1 minus 1 over 2 to the n. Now leave it on the bottom, because it helps to do the limits when you leave it on the bottom. Okay, the limit as n approaches infinity of 1 is 1, right? Because the graph of 1 as you approach infinity is going to keep staying at 1. But the second term, if you plug infinity in here, you're going to have 1 over infinity. And in limit land, what does 1 over infinity equal? 0. 1 over a billion, 1 over a trillion, 1 over a Google is 0. Getting closer and closer to 0. So this is equal to 1 minus 0. So we do have a sum of 1, which means that it is going to converge. And that's the door. The 1 is the door, getting to the door. Okay? Okay, let's do the same thing for the next one. All right? I prefer to work with fractions in this case because you can see the patterns better. What is the first term as a fraction? 9 over 10, agreed? 9/10. What's the next term as a fraction? 9 over 100. Then 9 over 1,000. And 9 over 10,000, agreed? Okay. Let's see if we can come up with the sum of this. What's the first term going to be? 9 over 10. Now add the first two terms. 99 over 100. Okay? Because this is 90 over 100. This is 9 over 100. 99 over 100. What's the next term? The next sum going to be? Add that to the next one. 999 over 1,000. And then it's going to be 9999 over 10,000. Agreed? Okay, let's write the rule. Are the denominators still the same? Yes. So we're going to put 10 to the n is how we do that. Now they didn't have that before, but do you see how I got that? I kind of jumped the gun there a little bit. This is 10 to the first, 10 squared, 10 to the third, and 10 to the fourth. They're all powers of 10. How do I write the top?
10 to the n minus 1.
10 to the n minus 1. Very good. So can I break this into two separate fractions like the last one?
Yes.
Yes. So it'll be 1 minus 1 over 10 to the n. So it will be 1 minus the limit of that second fraction is 0 again. So the answer is 1, and this sequence does converge. Yes?
Is it a coincidence that they both had the same as Sn?
Yes. It is a coincidence. Okay. Now, this actually proves that 0.9999999 out to infinity equals 1. Well, the limit is 1. Have you ever had that argument with somebody? Does 0.9 repeating forever equal 1? Is it the same thing as 1?
Yes.
I don't think it is.
That expression.
The limit is 1, but it doesn't equal 1. That's just me. Okay. All right, let's take a look now at this box at the bottom. And basically what this is properties of the way sums of series work, okay? It says if we have two convergent infinite series, in other words, this series, this sequence A sub n adds up to be A, and this one B of n adds up to be B, and then C is just a constant real number. First of all, look at this first one. If you put a C inside the summation, it's just C times the answer. So basically, like an integral, you can pull it out, okay? Because an integral actually is a form of a summation, if you think about it. The second one says the summation of two different series, A sub n and B sub n, is just the sum of their answers. And then the difference of two series is the difference of their answers. Does it say anything about multiplication and division?
No.
No. So don't assume that if you have AN, BN in here, you're going to get A times B. It doesn't work that way. It only works for addition and subtraction. Okay? So that's just something to know. Put a star by that. Future reference, I don't know if you're going to need it, but it's there. All right, turn to the back of this page for me, please. All right. Now, why are we learning this stuff? Okay, that's the whole point. Now we're going to talk about what the goal of this unit is all about, okay? We are interested in whether infinite series converge or diverge, because down the road in college level mathematics, you're going to need that information to be able to do things specifically with convergent series, okay? So, in order to determine this, we will have a series of convergence tests, and your flip book, most of the tabs are different kinds of tests. Notice that they're labeled with tests, this test, that test, the other test, etc. We're going to be learning 1 to 2 every day, and which one you use is based on sometimes the kind of series that it is. So if it fits this mold, you use this test. If it fits this mold, you use this test. And eventually you're going to have to be able to know which series test to use when, okay? So a convergence test is a procedure you follow that will determine whether or not a series converges. It does not tell you what it converges to necessarily, just whether in fact it does converge, okay? Now, get your flip book and open up to the page that says can, because I want to talk about that briefly. I have a friend who teaches BC Calculus in Austin. She's been teaching it for a long time. And she and I have been in contact this year, and she said, I've decided after grading the BC test for many years, I've been grading the AB test, so I'm not as familiar with the BC as far as the grading goes. She said, one of the things kids get marked off for is not writing down what test they use when they test for convergence. And that is being graded on the exam. So what she did is she came up with this acronym of CAN, C-A-N. Anytime you perform a test, you must show that you can do them. The C stands for the conditions. In other words, what has to be true about this series in order to use this test, okay? And then 2, the A is the apply. You apply the parts of the test. You take the limit, you divide these two things up, whatever it says to do. And then 3 is to name what it does, converges or diverges, and by what test you used. So when we're done, we have to write, therefore, this thing diverges by this test, or therefore this thing converges by this test, and you have to write it that way. So we're going to start off from the bat doing it that way every time. Check the conditions, apply the test, and then write down what your results are, okay? And make sure we do it the same way every time, okay? So that's the way it's going to be set up. So now we go back over here. The one thing I want you to underline under here that says this: there is no one test that will determine convergence for all series. That's why we have so many. There is not one that works for everything. It works based on what it looks like or how it's constructed. And as you get to the end of learning all of these tests, there will be some that you will like better than others, and you will use them more than others. A lot of times the AP exam does not specify that you must use a test, a specific test. You use the one, there may be 2 or 3 you can choose from, and you pick the one you like the best. And they'll give you the same results, okay? Now, one test might tell you that we're not sure if it converges, or it might converge. And some tests will tell you it definitely diverges, or it definitely converges, okay? Got to be careful to not say on a specific test that it does converge when all it proves is that it might converge. Okay, so we're going to talk about that test first of all. So the first test we're going to look at is the nth term test. This is first box. Okay? And we've actually used this a little bit already, okay? If the sequence, in other words, the term in the sigma thing, does not converge to 0, the series will definitely diverge. So basically what this does, it's a filter. It filters out all the ones that are going to diverge. So what you do is you take the limit as n approaches infinity of what the sequence formula is. Not the series one that we built, but the one that's written inside the sigma. If it doesn't equal 0, it diverges. Okay? If it equals anything else, it might converge. That's what the next thing says. If the sequence converges to 0, the series could converge and another test is necessary. So, what we're doing is just saying, if it doesn't go to 0, definite divergence. If it does go to 0, then we're going to have to try something else. Okay? Now, on the flip side of the coin, if the series converges, then the sequence will definitely converge to 0. So we're flipping it around. If it tells you that the series converges to 0, then the sequence, that the series converges, period, then the sequence will definitely converge to 0. Okay? Now, let's go look at it in the flip book, because my friend wrote it just slightly different. And this is really good. It says the nth term divergence test. This tells us nothing about convergence. Only a might, only a maybe. So what do? You take the limit as n approaches infinity of a of n. And then if it doesn't equal 0, then you can immediately say it diverges by the nth term test. That's what you write down if you get an answer besides 0. First of all, it says this test is a great time saver. Always do this first. Look at the problem and see if it goes to 0. And eventually you'll be able to look at it without doing a whole lot of math and know. And second of all, if it does equal 0, we have to keep going and do a different test after that. All right? So put that aside. We're not going to go through the rest of this at the bottom. We're going to go on and do some practice problems. And you can read that later if you so choose. Okay. Take a look at right above number 6, where it says, when you encounter a series in explicit form, like this, and are asked whether it converges, sometimes it helps to generate a few terms to get a feel for it. So what we're looking for is not what does the sum do, but what do the terms do individually. Okay? So because I can't take the limit of that really easily, I'm going to write out a few terms and just see what's going on. The first term is plugging in 0. When you plug 0 into here, what do you get? 4. When you plug in 1, no, you don't get 4. What do you get? 4 to the 0 is what? 1. I heard somebody say 4, and I went with that. 1 plus 4 is the next term. What's the next term after that? 4 squared is what? 16. Does anybody know what 4 to the third is? 64 plus ... Is that going to, are the terms going to get closer and closer to 0? No, the terms are just getting bigger and bigger and bigger, aren't they? So we say that the limit as n approaches infinity of 4 to the n does not equal 0. Therefore, it diverges by the nth term test. That's how you write it in AP form. You show me that the limit is not 0, therefore it's going to diverge. The only one you can quote the nth term test on is if it diverges. All right? Now, this one, if I took the limit right now of this, I could get a very quick answer. 1 over n. That's going to 0, isn't it? So, do I know for a fact that it's going to converge? This test tells us nothing about convergence. It just tells us that it could converge. So all I can write here is could converge, and eventually I'm going to show you some different tests to know whether or not it does. Right now all we can say is yes, it's divergent or it's a maybe converge. That's our only two choices today. Okay? Now the next one, we have never done a limit with a factorial before. Okay? That's brand new stuff. So what we're going to do is look at this by numbers. Okay? Plug 1 into both of these. Top will be what? 3. Bottom will be 1. Plus, go to the next term. 6 over 2 factorial is 2. Third term. 9 over 3 factorial is 6. And then let's go one more. That's 12 over 24. Okay. Now we're going to do this one a little more implicitly. Okay? So let's simplify each of these and see what's going on. 3 over 1 is 3. 6 over 2 is 3. What is 9 over 6? 3 halves, which is 1.5. And what's 12 over 24? 1 half. Do you believe these fractions are getting closer to 0? Yes. Will they ever go negative? No. Okay? So, this one is approaching 0. Okay? So we can say now that the limit as n approaches infinity of 3n over n factorial is 0. These fractions, each one individually, or these numbers, are getting closer and closer to 0. So then we can say that it could converge. That's all I can say at this point. I can't say for sure that it diverges. Now, why are the fractions doing that? Let me just kind of point something out. The tops are growing, the bottoms are growing, right? But who's growing faster? The bottom is. Anytime the bottom grows faster than the top on a fraction, it's going to converge. Okay? All right, let's move on. The next test that we're going to look at is what's called a telescoping series. Now, y'all know what a telescope is, right? It expands out so you can see it. Now, telescoping in this case is it looks like it's tiny, but it actually expands out into something that's rather big, and you're going to see what happens when it does. Okay? This is a potential test to see if something does converge after this one. So what I'm going to do is look at this series right here. It's 1 over n minus 1 over n plus 2. All right? So what I want to do is, first of all, apply the nth term test that we just did. What is that first fraction going to approach? 1 over infinity. That's 0. What about the second fraction? 0 again. So this one, it does equal 0. So it might converge. Okay? It might converge. So what we're going to do now is we're going to write out a few terms. So we're going to plug in 1 first. Go back up here. So that's going to be 1 minus what? 1 over 3. Agreed? Then the next term is 1 half minus 1 over 4. The next term is 1/3 minus 1 over 5. And the next term is 1/4 minus 1 over 6. What's going to happen to some of these terms in here? Look at the 1/3. What are they going to do? They're going to cancel. What about the 1/4? Are they going to cancel also?
Yeah.
Now, I didn't write it down, but what would the next term be? 1 over what? 5 minus 1 over 7. So the 1/5 would then cancel, wouldn't they? So every time you write a new term down, something cancels out. Are you following what I'm saying? That's what a telescoping series does. As you write it out, stuff starts canceling out. Okay? And when you're done, when you get to the end, you eventually get to a point where you only have a couple things left on the end and a couple things left on the beginning, and that's it. Sometimes it's only 1 and 1. Okay? So, what's going to be left on the front end of this thing?
1.
The 1 is, and the 1/2. Nothing's going to cancel with the 1 or the 1/2. Okay? Now the very last term is going to have nobody to cancel with. Do you agree with that? So the last term is, save some room, 1 over n plus 2 is the last term. Now notice it's the first thing in each of these two parentheses, so it's going to be the last thing in the last two parentheses. So the last one here is going to be 1 over n plus 1, the one right before it. Okay, so even though this is infinite, after all is said and done and everything cancels, that's all that's going to be left. 4 terms. Yes, ma'am?
How come you wrote minus signs instead of plus signs?
Because they happen to be the second term in each parentheses. And the second term in each parentheses is negative.
So is it always going to be positive, negative, negative?
It's positive, positive, negative, negative.
Oh, yeah.
Okay. Are you following me how I'm getting the n minus 1 and n plus 1 and n plus 2? Kind of, sort of? Okay. So, now, can I take the limit of that? If I take the limit of this, this is what it is converging to, if I get an answer. So the limit would be 1 plus a half minus, what's the limit as n approaches infinity for this fraction? 0. What about the next fraction? 0 again, so my answer is 3/2. So that whole sum adds up to be 3/2. Therefore, it converges by the telescoping series test. And you have to write that down. Yes, ma'am.
Did you plug in the infinity to the 1 over n plus 1 and the 1 over n?
Yes, because right here it told me to take the limit as n approaches infinity. Because that's saying as we get infinitely big, those two fractions are getting closer and closer to 0. Yes?
Can we just call it the telescope test or something? Or do we have to write the whole thing out?
I would write the whole thing out, but I'll check on it. For now, say the whole thing.
Is it converging at 3/2?
It is converging at 3/2 because we did find the sum. They're not as concerned as to what it converges to because not every test tells us. This is one that happens to tell us. But it does converge. Okay? So now look at the one here. Here is a simplified version of what a telescoping series looks like. A1 minus A2 plus A2 minus A3 plus A3 minus A4. And notice that practically everything in the middle is canceling except for the A minus 1, A to the n plus 1 over here and the A1 on the front. And then the limit tends to be just A1, okay? It'll be whatever it comes out to be. Now, we're going to do one last problem. Here is a telescoping series, but it doesn't really look like one. This kind of problem here, where it's two fractions with ends on the bottom, that's usually telescoping, especially if they're subtracted. This one is telescoping also, but it doesn't look like it. So we have to do partial fractions. Let's go back and review that real quickly. So, we're going to recopy the sigma, n equals 1 to infinity, and we're going to write what the two things factor into. How does 4n squared minus 1 factor? These are difference of two squares. 2n plus 1, 2n minus 1 is the answer. That's what it factors into. Now I'm going to write that down here as well, because I've got to do the cover-up thing, the Heaviside method that we learned. Okay, let's review how to do this. First of all, take the first denominator. What would make it 0? Negative 1/2. So go to the other fraction, cover that one up, plug in negative 1/2. So that would be a 4 on top. 2 times negative 1/2 is negative 1, minus 1 is negative 2. So that means this one is negative 2 right there. Does this sound vaguely familiar? Yes? All right, do the same thing to the other fraction. What causes the second fraction to be 0? Positive 1/2. Cover it up. So that would be 4 over 2 times a half is 1, plus 1 is positive 2, which makes that a positive 2. So now, because my numerators are opposite signs, it's going to be a telescoping series. So before I go any farther, I need to switch them. N equals 1 to infinity. I want to put the 2 over 2n minus 1 first. I want them to be subtracted because it makes all the canceling look much nicer. It works out nicer if you do it this way. So what you need to do is write out a few terms. So we're going to plug in 1 and see what happens. So that would be 2 over 1, right? Minus 2 over what? Plugging 1 into this denominator. 3 plus this would be 2 over 3 minus 2 over 5. Oh, look, 1, 3, 3, 5. Do we see a pattern brewing here? 2 over 5 minus 2 over 7 plus dot, dot, dot. Okay, now let's go ahead and write down the last one. 2 over 2n minus 1 minus 2 over 2n plus 1. Okay, now, it's always a good idea to write the last one down. All right, let's start canceling. So the minus 2/3 plus 2/3, minus 2/5, they're immediately after the previous one, right? So the minus 2/7 will cancel with a plus 2/7. And the way it works is this. If on the front end, the first one is still there, on the back end, the last one will still be there. It's one of each, okay? Because everything in the middle will cancel. So we're going to now take the limit as n approaches infinity of the first term, 2, minus the last term, 2 over 2n plus 1. If there's only 1 on the front end, you get 1 on the back end. And it's the last one. So it's the first one on the front, last one on the back. So the limit as n approaches infinity of just a 2, it's just 2. What about the fraction? As n approaches infinity, the fraction goes to 0. So the limit is 2. Therefore, the series converges. I didn't have to write series, I just did. By the telescoping series test. Because I got an answer. Yes, ma'am.
Did you cancel out the 2 over 7 just because you knew it would cancel eventually?
Yes. I knew that the 2 over 7 would cancel with the very next term because it would be 7 and 9.
And then the last 2 terms you wrote, is that just because you copied it from?
I copied it from here, yes, because that's going to be the last ones. And since 1 was left on the front end, that means the back end will have 1 left as well. I don't write both of these down here, I only write the last one. That's why I only brought the last one down. Okay, so if you go look in your flip book, here's the telescoping page we put in there. It shows you what it looks like. We need to make a change, so please open your flip book up to the telescoping page. There is a boo-boo on it. This says A of n expands to B1 minus B2 plus B2 minus B3. No, B of n. Make that a B right there, please. That's B of n. Okay, so let's use this as another practice problem real quick. Notice what's in here, all right? What is not going to cancel on this end? Just the 1. So the only thing not going to cancel on the other end is the 1 over n plus 1, the last term, okay? So then you take the limit of that, so it's going to be B1 plus the limit of the last term, which usually comes out to be just B1. Okay? So that's going to be 0. Then you write down that the sum converges to S. Now you don't really have to write 2S. You just have to write that it converges by this telescoping series test. All right? Yes?
So you changed the B, the A to a B.
That needs to be a B. That's all I changed. All right? Any questions? All right. Awesome job.